Say you're watching tennis and you want to know what's going on within a close match. Well, that's where an agent-oriented architecture comes in. It's a real-time interactive AI assistant powered by an agentic graph. Such a system was debuted at the 2025 Wimbledon Championships and the US Open 2025. Now, this assistant, it allows fans to ask live questions during singles matches and to get instant and insightful answers right at your fingertips. Now, here's an example path to the experience. So the user, what we can do is we can select a match that's either in play or scheduled to play. Now, the system, it supports conversations about in progress, retired, suspended, or even completed matches. But when the system is available, that any fan can then begin a dialogue. They can start a dialogue by pushing one of these buttons, and let's say we want to push a match chat button underneath the tennis match that has the score. You can also follow live or view a recap if you want, but in all of these cases, we follow an evidence-based user experience. Now the real fun really begins. So upon entry, the user is then gently nudged into a conversation with two pre-curated entry-level questions, often around match-defining skills or even pivotable plays. This is called classic UX priming. So we want to lower the barrier for engagement, but spark your curiosity and invite participation throughout a match. But of course, the more inquisitive minds, they might want to ask any question. And this is where this open field comes in, where you can click and then it'll open up and you can put in any query that you can think of. With the user's question in hand, or maybe even this button pushed, the system transitions into this agentic experience, launching this decision tree interaction. The user selects a primary category from the following, right? Now, a user doesn't have to select this because, again, they can enter any question that they would like to, right? And whatever query you entered, it's dispatched to a scaled out cloud-based system of systems. And it's really optimized for this real-time analysis and insight generation. But even if no subcategory is chosen, we do invite the user to maybe have a dialogue or a question answer with the system to ensure that no curiosity goes unanswered here. Now comes the moment of computational ingenuity. So here, a visual indicator, it appears whenever you submit a query, showing that the LLM is either thinking or it could be running. That this is where you have the chains of thoughts that are being fed back into the model itself. Another aspect or state that happens is called fact checking. So we want to make sure that anything that's returned back by this real-time system, it's accurate. But this small touch, it really adds what's called transparency to the AI's cognitive process and maintains all the user's engagement throughout. But importantly, this experience is also seamlessly mirrored across both mobile and desktop. So it provides you this consistent and device agnostic interaction model, whether you're maybe sitting on the phone in a bleacher or a stadium, or you're in a laptop at home, but the system is anywhere you are, it's ready on the go, and it's right here for you. Now let's take a look at the architecture behind this system where it balances scale, response time, and AI accuracy. So here's the masterpiece. So at the foundation lies a robust event-driven architecture that's built on this publish-subscribe messaging system. So as a match progresses here, it ingests scoring and performance data all the way through to create these different feeds. Now, this data is immediately published to on-demand topics, enabling this near real-time availability. So simultaneously, the system writes dozens of these JSON files into these cloud object stores buckets that are fronted by CDNs. This ensures high-speed global distribution and caching. Now, once a user submits a query here, the message traverses the secure firewall CDNs and it finally lands in this containerized application known as a middleware app. This is deployed across a distributed cloud infrastructure across multiple regions, and it has 30 active replicas. The middleware app, what it does is it takes the question and it first analyzes and it interprets it. So first we have this mini LM L6v2. It's this model that has embeddings and it transforms the query into numerical vectors. Now, these embeddings are then passed through a random forest of 100 different decision trees, which classify the question into specific tennis categories, such as the player stats, the match logistics. You might even have questions about live insights. But based on this confidence, the thresholds that we have empirically determined, we then in turn go through and we want to know how confident is this model that this question is about a particular topic. So as it goes through the pipeline, we then need to ensure that the conversation, it remains safe and respectful. So this is where we screen all the questions through this HAP, which stands for hateful, abusive, profanity filters. And we then take that and we go through, and once we've classified and we've gone through that moderation step through all those gates, we then can go to the next step. And this is where the system reaches a decision point. If the question fits in a known, confidently classified category, we then go into this custom extension that's right here. Now, if the confidence is low, or the anomaly detector, it flags ambiguity, or the question is then can be routed to this knowledge-based system, which is almost like a fallback system. And this is deployed into 2 different regions. But here, this fallback system, it consults a library of about 50 different intents that are mapped to topics, which then return thoughtful and pre-trained responses. For example, if you're asking, where can I go find a place to get tickets? Or where can I find shade? That might go to our knowledge base. But in most cases, this includes a deep link to the relevant tennis data, and it closes the loop so that the UX, it shows and renders the appropriate context. So when a query does meet all these routing criteria, it's then sent to this custom extension application here. And this is a powerhouse app. It runs on over 60 replicas across a multi-region Kubernetes platform. So here is where then the traffic is routed to this lane graph. It's pulled from a queue. So we initialize many lane graphs at the same time, right? And if one isn't ready, the system then waits until one does become available. But once initialized, and we have this agentic framework, we then can execute the following steps, right? And these steps, it uses a bunch of tools to go out and it pulls in information such that we can extract the relevant information that's about the question that we've already classified. Now, this data is formatted in 2 different ways by the tool. We can have raw JSON, which preserves the original schema and the keys that came from the tennis information. We also have an LLM JSON, which is more of a decorative type text, and it helps to prime and optimize LLM comprehension of what this data is about. And then we go into the generative agent part, and this is where the structured data to the formulation of the answers comes into play. So if the agents determine that they can't confidently respond from all this information, maybe it could be due to insufficient data, or maybe the play hasn't caught up, right, to what the person is asking about, then we will notify the middleware application. This is when there's no structured or generative agent can really provide a cohesive answer. We then go to what's called a light synthesizer that's invoked as a last resort. This is what we call a lightweight LLM prompt, where we attempt a final synthesis of the information of any data fragments that still remain throughout this pipeline. And through all of this, the architecture balances scale, speed, safety, as well as accuracy to provide a nice experience to you. At the core of this lies an agentic system architected as a directed graph. Now, in this graph, each agent is represented by a discrete computational agent that looks like a node. And each of those nodes is connected by an edge. And the edge means information flows in between the agents here. Now, the process begins at this initialization agent here. This creates and it propagates a state variable. So this is a dynamic context object that goes throughout this entire graph. But one of the earliest agents is called the tool agent here. It interprets the conversational category signal, and it selects the appropriate data feeds for extraction. Now, this feed, it derives data from all the tennis state, and it then saves it into the shared state for downstream agents. Now, the next critical node in all of this is called the facts agent. This performs parallel inference operations using 2 different types of thread, right? So you have thread 1 and thread 2, right? So the first thread, what it does is it constructs a prompt. It includes a persona, right? So it tells it how to act and how to respond, the style it's supposed to use for the extracted JSON data that it pulls out. It then submits it to an LLM to produce a paragraph interpretation directly from the input. Now, your thread 2 here, what this does is it uses a synthesizer, right, that generates standalone factual sentences. And these sentences are then fed into another LLM. And it's almost like a race. So the first one that wins is then used in the propagated piece of the graph here. Now, to manage the response latency and to ensure that the system responsiveness, each path of these, it operates with strict timeouts because we want to be really fast so that users can see what the output is going to be. So the framework allows for up to 3 different potential outputs in order of preference. So the first one would be the direct JSON interpretation into a coherent paragraph. Now, the next one that we try to achieve would be a summarized paragraph from multiple factual sentences from one of these threads that, again, is racing over time. And that's what one of these summarized agents, what it does. Now, a collection of these, it goes to a judge here, right? So that we then in turn can figure out what is it supposed to say, what is it supposed to do, right? And if it determines, wait a minute, this content isn't exactly right, then it's going to feed back into a corrective type agent here, right? So we have these 4 agents all working together to produce this said output, right? And all the candidate outputs are then routed, right, all throughout down into this lower section here, so that we then in turn can produce the content. But I want to revisit this judge agent, because what it does is it then in turn, it evaluates the content on 2 primary dimensions. The first one, it needs to make sure that the content that's produced is factual, right? But it's also relevant to what the user has been asking about from the initialization to the tools agent. Now, if it does identify uncertainty and the preferred output, it may pre-append, confidence adjusting a preamble, right, to the response. And then once judged, it might go into a corrective type agent here, right? And the corrective agent, it'll enforce the textual consistency by aligning the response to predefined stylistic guidelines that might have been supplied by the tennis user. Now, if the agent pipeline, if it fails to produce a valid, even a confident output due to maybe missing data, it could even be an ambiguity or even timeouts of these threads that are constantly running in the background in arrays, the system, it can activate a fallback search mechanism across a knowledge base. But should this too return no useful result, the system performs this final synthesis using a lightweight LLM-based synthesizer to generate informative responses. Now, these final informative responses, they sometimes go down here, right? And when this does happen, we then can return that back, right, to the user. But these final contingencies ensure that the system maximizes response coverage, but it also is highly accurate so that we can provide to the user an answer that aligns towards what they're asking for. So now let's look at some of the streaming data. The real-time live likelihood to win estimation within our system is enabled by a streaming data architecture and probabilistic modeling framework. Now, this system integrates predictive analytics, live match dynamics, and event-based computation to generate and update this likelihood to win estimates all throughout the duration of a match. Now, what happens is, prior to the first serve, we have a pre-match likelihood to win that looks very much like this, a donut plot. But this model, it's a predictive model, right? And it gives you a probability of a player winning before a match starts for each of the players. Now, we have a model that's been built on a couple features, right? Some of them are around head-to-head history between the players. Now, if they have the head-to-head history, if not, then we'll go to other predictors. Now, we also have forecasted play indicators and historical match outcomes that all go into this. So, for example, in a specific match scenario, I might have a model that predicts player A to have a 53% likelihood to win, and I might have player B that has a 47% chance likelihood to win. Now, this close distribution, it indicates a statistically balanced match, right? That could happen. And what the models are doing is it's applying this probabilistic equation where we want to make sure that we can get the odds of a player winning given the evidence that I just showed you. Now, as the match progresses, we have this live likelihood to win that looks like this. Now, the system, it transitions to this live likelihood to win every single point. So it's continuously updating the probability model using this real-time performance metrics. Now, the live likelihood to model, it is a time-defined model, which we have a decayed pre-match probability, which gradually diminishes the pre-likelihood to win pieces, right? So as a match unfolds, we then in turn say the match data that's happening in real time matters more. And then we also have a booster function that's activated by critical match events. This approach, it enables the system to account for both the historical expectation and the real-time player dominance that's happening. Now, in this 5-set match, which you can see the score right here, the player with the pre-match edge up here had a 53% and ultimately did win 3-2. But you can see the story as it was unfold that it wasn't just a linear win, right? That one of the players had more momentum, and then it shifted back again, and then finally we get it right because we then in turn converge to what the ultimate player who won, which is player A, right? And this happened after a tiebreak in this dramatic sequence of events. Now, this visualization serves not only as a statistical output, but also as a narrative of the match's momentum. It captures competitive tension as well as the turning points within this high-fidelity, message-driven architecture. These insights are made possible by this messaging infrastructure that you can see here. And it's a pub-sub piece that uses what's called MQTT pieces. Some of this, it uses what's called a broker application that subscribes to match-specific topics upon scheduling. And then as each of these scoring events occurs, the data is published to each of the relevant topics that we have. So it's highly parallelized so that it's very fast. And we retrieve these messages here, right? And then we pass it to an engine. And this engine is what uses some of these equations that I went over to create, right, these numbers here that we have. But each scoring update, it triggers the recalculation of this live likelihood to win at that moment in time of play. And the resulting value is serialized and stored, right, over into a CDN and a cloud object storage, enabling this asynchronous access from our fans all around the world. So when a fan asks a question, through our agentic system about live or past win probabilities, the system performs some of the following steps. So first we'll go and we'll retrieve, right, the relevant JSON likelihood to win data that's been created, by this system here. And this utilizes the data extractor agents to transform the data into the semantic objects. And we in turn submit all of the summarized data to an LLM. And this integration ensures that fans now receive intelligible, data-driven responses grounded in the probabilistic analytics and powered by this real-time computational system that we have here. Now, the agent-oriented system, it delivers a real-time intuitive experience by combining the live scoring data with this AI pipeline that interprets fan queries and updates the match insights like momentum shifting and the win predictions. But by this blending the AI and streaming data, and we combine Gen AI with predictive modelings with this smart UX, this is how we transform that raw data into clear, engaging narratives for tennis fans all around the world.